Hello everyone. So in this lecture we'll talk about unstructured quantum search, or what's called Grover's algorithm for database search. So the problem we are trying to solve is one of looking for a needle in a haystack. Of course, in this case our haystack and needle are digital. So what does a digital haystack look like? So think of it this way: you're given a table with n entries, and one of these entries is marked. So there's a particular entry. If you look inside this entry, you'll know this is the entry you're looking for, and your goal is to find this special marked entry. Now, how can you try to solve this problem? Of course, classically, you might try probing every entry in turn, and this would take you n steps. But instead, you could do a little better if you probe random entries. Well, then the expected amount of time before you hit the marked item, assuming there's a single one, is n/2 tries. So the question we are going to be asking here is there a way of doing this, solving this problem much faster than this using a quantum algorithm? Okay, so this is the image that we have in mind. That there's some way that you could look, instantly get into this haystack and find the hidden needle. Okay, so before we do this, we want to, let's try to understand what the relevance of this looking for a needle in a haystack is. Well, it turns out that there are a lot of computational problems. In fact, the typical computational problem has this structure of looking for a needle in a haystack. So there's this whole class of problems called the NP-complete problems, and there are thousands of these kinds of problems that have been identified as being and proved as being NP-complete, but identified as being extremely important problems. Okay. In fact, there was some compilation which said that over the last decade or two, there've been thousands of these problems that have been identified in the physics and chemistry literature alone. So what are these NP-complete problems? These are computational problems for which finding the answer is difficult to this computational problem. But once you've found it, it's easy to check that you found the correct answer. So here's the iconic example of an NP-complete problem. It's called satisfiability. So you're given a Boolean formula over n Boolean variables. So it's a formula which says either x1 or is true, or x2 is false, or x3 is true, and x2 is true, or x5 is false, or x6 is true, and so on. There are a number of clauses of this kind. You have n such variables, and you want to know, is there an assignment of true and false to your n variables which makes this formula evaluate to true, which makes every clause evaluate to true. So notice that there are two properties of this kind of a problem. The first is that the number of possible answers is very, very large. It grows exponentially in the number of variables, so it grows like 2 to the n, because each variable can be assigned either true or false. The second property is that once you actually find a solution, so if you find an assignment that satisfies every clause, then it's easy to check that you have indeed found the answer. And so in this sense, solving this problem is like finding a needle in a haystack. Okay, but how does this satisfiability problem correspond to this searching of the digital haystack, or of this unstructured search problem. So, well, let capital N be 2 to the little n. So there are 2 to the n possible truth assignments that you can make to your n Boolean variables. So think of each entry of this table as corresponding to a particular truth assignment x. Okay, and now mark each entry. Let the contents of each entry be either that the assignment is a satisfying assignment, or that it's not a satisfying assignment. So now the kind of question we are asking is, well, the marked items correspond to those assignments which satisfy this Boolean formula, and what we are looking for is one such assignment. So we are looking for a marked entry in this digital haystack. Okay, so how would you go about trying to solve this quantumly? Well, here's the tempting thing. Why not try to use the fact that you have an exponential superposition to probe all these 2 to the n entries in parallel in different quantum universes, so to speak. So in other words, we all know that we could take n qubits, little n qubits, where 2 to the little n is capital N, and we could put them in an equal superposition over all n-bit strings, so all numbers between 0 and capital N minus 1. So we start in this, we could use a Hadamard transform and create this superposition sum over all y equal to 0 to n minus 1 of 1 over square root n y. And now we go ahead and probe the yth entry of our table. If you want, remember what this digital haystack corresponded to. So let's write it down here. So remember we had some Boolean formula f of x. We are thinking of x as x1, x2 through x of n as n bits, and f of x was some Boolean formula which was, say, x1 or x2 bar or x3 and so on and so on and so on. Okay, so it's an AND of a bunch of clauses, and we think of f of x as either being 0 or 1. And so now what we would do is we just feed this into some circuit which computes f, and our output would be, of course, a superposition over all y of y f of y, right? And now, okay, it looks like we've computed f in superposition, and now couldn't we reach in there and pick out a satisfying assignment, a y such that f of y equal to 1? But think about it, that's not how quantum mechanics works, right? Remember, we had our rules of measurement. So if we do a measurement, so what happens if we measure? What happens is, what's the chance we see f of y equal to 1? Well, remember our rules of measurement. It's the same as though we measured everything. We measured all our input, all our qubits, and then it's the chance that f of y equal to 1 if we measure all the qubits. But what happens if we measure all the qubits? Well, when we measure all the qubits, we see a uniformly random y. So we see each y with probability 1 over 2 to the little n. And so the chance we see f of y equal to 1 is exactly the same as the chance we'd find a satisfying assignment if we probed a random entry of the table, or the chance that we'd see a marked item if we probe the random entry of the table. So unfortunately, this way of doing things is no better than probing a random entry of the table. Okay, so remember, what gave quantum algorithms all its power was not just the fact that we could get a superposition that was spread over 2 to the n different choices. That's not yet enough, because we can do something like that probabilistically. So if we pick a random entry, if we sample uniformly, we could think of that as having a probability spread out uniformly over all these exponentially many choices. What makes quantum computing unique, what gives it its power, is not only the ability to do that, but also then later to get constructive and destructive interference. So we want to get constructive interference only at those strings which correspond to answers to the problem that we are trying to solve. Okay, so this is what we're really trying to do next. So what we want to know is, can we actually come up with a better kind of algorithm, an algorithm that quantumly somehow probes this digital haystack in time which grows not like capital N over 2 as in the classical case, but like log of capital N, or polynomial in little n, right? That would be the ultimate goal. Unfortunately, there's a theorem, okay, that we can prove, which says that any quantum algorithm to solve this problem of finding a needle in a digital haystack must take at least square root of capital N time, where square root of capital N is now 2 to the little n over 2. So it's exponential time still, even though this is okay. So 2 to the n over 2 is still exponential in little n. So this is something that we actually proved way back in 1994, around the same time as Shor's factoring algorithm. So given this theorem, which says that there's really not much, that you cannot get an exponential speedup for searching for a needle in a haystack, and to the extent that the NP-complete problems are really well modeled by digital haystacks, that you cannot get an exponential speedup for NP-complete problems, then Shor's algorithm for factoring was somehow the best we could have hoped for. So it came as a really pleasant, an unexpected, pleasant surprise that quantum algorithms were this powerful. This was really a remarkable discovery. Okay, a couple of years later, there was this beautiful algorithm that was discovered by Grover, which showed that, in fact, you could get this quadratic speedup. So you can't get an exponential speedup for unstructured search, but you can get a quadratic speedup over the best classical algorithm. And you can solve this problem in square root of n steps. So let's again be clear about the problem that we are solving. So the problem is, we are given a function from 0, 1 through 0, from a domain of size capital N to 0, 1. And the challenge is to find an x such that f of x equal to 1. The hardest case, of course, is when there's exactly one needle. So you're looking for, there's exactly one x such that f of x equal to 1, and you're looking for that one. Okay. So once again, the way to think about this problem is, you're given a program for for computing f. So you're given some circuit C sub f, which takes as input n bits and outputs a single bit f of x. So it takes as input x, outputs f of x. And equivalently, of course, you can transform this into a quantum circuit u sub f, which takes as input x, outputs x, it takes as input x and 0 and outputs x and f of x. Or if you want, you can actually let the input, you can say it more generally, and if this answer bit initially was b, then your output bit is b exclusive or f of x. So it toggles a bit if and only if f of x equal to 1. What we are assuming here is that you cannot look inside the circuit. The circuit is given to you as a black box, and you cannot look inside this quantum circuit either. So all you can do is give it an input and see what the output is. Of course, in the quantum case, you can not only give it an input x, but you can also give it an input sum over all x. So a superposition over all x. And then your output is a superposition, the same superposition over all x of x, f of x. Okay, so in the next video we'll see how to actually get this quadratic speed up for this search problem.